In the quiet halls of the Institute for Advanced Study in Princeton, New Jersey, a young physicist named Helen Wong stared at her equations with growing disbelief. The year was 2023, and what had begun as a theoretical exploration of quantum gravity had led her to a startling possibility, one that seemed to defy common sense. "That cannot be right," she whispered to herself, yet the mathematics refused to yield a different answer. For over a century, scientists had revered the cosmic speed limit established by Albert Einstein's theory of special relativity, 299,792,458 meters per second, the speed of light in a vacuum. Nothing with mass could reach this speed, let alone exceed it. This principle had stood as one of the fundamental pillars of modern physics since 1905. Yet Helen's equations suggested something astonishing. In the grand cosmic perspective, light might actually be crawling. To understand this counterintuitive idea, we need to step back and examine how our understanding of speed and motion has evolved throughout scientific history. In the late 1600s, Isaac Newton had established a view of the universe where space and time were absolute. In this framework, objects moved through a fixed, unchanging stage called space, and time flowed uniformly everywhere. Speed was simply how much space an object covered in a given time. This view seemed intuitive and aligned with everyday experience. Then in 1905, Einstein revolutionized our understanding with special relativity. He demonstrated that space and time were not separate entities but facets of a unified spacetime, and that the speed of light remained constant for all observers, regardless of their relative motion. The implications were profound. Time dilation, length contraction, mass-energy equivalence, E equals mc squared, these concepts revealed that our intuitive understanding of reality was fundamentally incomplete. But Einstein did not stop there. In 1915, he unveiled general relativity, which described gravity not as a force but as the curvature of spacetime caused by mass and energy. This theory predicted gravitational waves, black holes, and the expansion of the universe, all later confirmed by observation. The expansion of the universe brings us to the crux of Helen's realization. In 1929, astronomer Edwin Hubble discovered that distant galaxies were moving away from us, and the farther they were, the faster they receded. This observation became the foundation of the Big Bang theory, formalized by Georges Lemaitre, which proposed that the universe began as an extremely hot, dense point and has been expanding ever since. But here is where things get truly mind-bending. The expansion of the universe is not like an explosion where galaxies fly through space, explained Dr. Brianna Kowalski, a cosmologist at the University of California, Berkeley, who had been corresponding with Helen about her work. Instead, space itself is expanding, carrying galaxies along with it. This distinction is crucial. When cosmologists say the universe is expanding, they mean that the fabric of spacetime itself is stretching. Galaxies are not moving through space, rather, the space between them is growing. The rate of this expansion has been measured with increasing precision since Hubble's time. The most recent measurements from the Planck satellite mission, completed in 2018, put the expansion rate, known as the Hubble constant, at approximately 67.4 km per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, of distance, galaxies appear to recede from each other at 67.4 km per second faster. This value might seem small, but its effects compound over vast cosmic distances. At sufficiently large distances, galaxies appear to recede from us faster than the speed of light, Brianna noted. This does not violate special relativity because the galaxies are not moving through space faster than light. It is space itself that is expanding. According to current observations, objects located approximately 14.4 billion light-years from us in what astronomers call proper distance are receding at the speed of light. Beyond that lies the cosmic horizon, a boundary beyond which we can never observe, even in principle, because light from those regions can never reach us. But the expansion continues far beyond this horizon. Current models suggest the observable universe is just a tiny fraction of the entire cosmos. Based on inflation theory, developed by physicists Alan Guth and Andrei Linde in the early 1980s, the universe might be at least 10 to the power of 23 times larger than what we can observe. Helen's insight came from considering the implications of this vast expansion. If we could somehow freeze the universe and place markers at regular intervals throughout all of spacetime, both observable and beyond, then release a photon and let it travel, that photon would only ever visit an infinitesimally small fraction of the markers, Helen explained. This is because while light travels through space at its immense but finite speed, new space is continuously being created everywhere. At sufficiently large distances, this expansion occurs faster than light can travel through it. Imagine an ant walking on a balloon that is being inflated, Brianna offered as an analogy. No matter how fast the ant walks, there are parts of the balloon it can never reach because the surface is expanding too quickly. In 2001, physicists Tamara Davis and Charles Lineweaver published a landmark paper in the journal Scientific American that clarified many misconceptions about cosmic expansion. They emphasized that the apparent superluminal recession of distant galaxies is a natural consequence of general relativity and does not contradict special relativity. Helen's work took this concept further. Using mathematical frameworks from quantum field theory and general relativity, she calculated the total proportion of the universe that light could ever reach, given the current understanding of cosmic expansion. The result was staggering. If the universe is as large as inflation theory suggests, then light, the fastest thing we know, can only ever traverse an unimaginably small fraction of it, perhaps less than 10 to the power of -23 of the total. In a sense, Helen said, light is almost standing still compared to the true scale of creation. This perspective transforms our understanding of cosmic speed. While light moves at 299,792,458 meters per second relative to local space, when compared to the full extent of what exists, it might as well be motionless. The implications extend beyond theoretical physics. In 2018, MIT physicist Alan Guth, who originally proposed cosmic inflation, along with colleagues published calculations suggesting that eternal inflation, a variant of inflation theory, predicts a multiverse so vast that it might be infinite in extent. In such a multiverse, light's reach becomes even more limited. If these models are correct, Brianna explained, then the fastest possible signal in physics, light, is effectively the slowest thing in existence when measured against the true scale of reality. This realization connects to another cutting-edge area of physics, quantum entanglement. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for their experimental work confirming quantum entanglement, a phenomenon where particles become correlated in such a way that the quantum state of each cannot be described independently of the others, regardless of the distance separating them. When measurements are performed on entangled particles, the results show correlations that seem to require information traveling faster than light. However, deeper analysis reveals that no actual information is transmitted superluminally. The correlations are built into the quantum state from the beginning. Nevertheless, entanglement hints at deeper connections in the universe that transcend our classical understanding of locality and causality. Perhaps the universe employs mechanisms beyond what we currently comprehend, Helen suggested. If light can only reach an infinitesimal portion of what exists, might there be other ways information propagates through the cosmos? These questions touch on the frontiers of quantum gravity, the as yet unsuccessful attempt to reconcile quantum mechanics with general relativity. Theories such as string theory and loop quantum gravity propose radical reconceptions of space and time at the smallest scales, potentially offering new perspectives on these cosmic questions. In 2019, physicists at the Perimeter Institute for Theoretical Physics published work suggesting that space itself might emerge from underlying quantum entanglement. If true, this would mean that space, the medium through which light travels, is not fundamental but emergent from deeper quantum processes. This brings us back to Helen's original insight: the limited reach of light implies that our fastest messenger is, in cosmic terms, remarkably slow. When Einstein formulated special relativity, he was considering motion through existing space, Helen explained. But general relativity and modern cosmology show us that space itself is dynamic, it curves, warps, and expands. This fundamentally changes how we must think about cosmic speed limits. The cosmic horizon, the boundary beyond which we can never observe, is currently estimated to be about 46.5 billion light-years away in every direction. This is much larger than the 13.8 billion years that have passed since the Big Bang because space has been expanding as light has traveled. Yet even this vast observable universe is likely just a tiny pocket in an immensely larger cosmos. Mathematical models of inflation suggest the universe could be at least 10 to the power of 23 times larger than what we can see, and possibly infinite. In such a universe, light speed, though enormous by human standards, relegates it to an almost stationary messenger when compared to the true extent of existence. It is humbling, Brianna remarked. For centuries, humanity has looked to the speed of light as the ultimate cosmic speed limit. Now we realize that in the grandest sense, light barely moves at all relative to all that exists. This perspective shift has philosophical implications as well. Throughout history, light has held a special place in human thought, from religious metaphors to scientific reverence. The finite speed of light, first measured by Ole Romer in 1676, has been a cornerstone of modern physics. Yet now we must grapple with the notion that this cosmic speed demon is, in the largest context, almost frozen in place. In 2016, cosmologist Max Tegmark of MIT published work suggesting that mathematical structures might extend even beyond the multiverse predicted by inflation. If reality is ultimately mathematical in nature, as some theoretical physicists propose, then the limited reach of light becomes even more profound. We might need to reconsider what we mean by fast or slow, Helen suggested. These concepts only make sense relative to some reference frame or standard of comparison. When we choose the full extent of reality as our reference, light is astonishingly slow. This does not diminish the importance of light speed in our local physics. Within the observable universe, nothing can transmit information or energy faster than 299,792,458 meters per second. This limit shapes everything from the behavior of subatomic particles to the evolution of galaxies. But zooming out to the largest scales forces us to reconsider our cosmic perspective. As Helen and Brianna's work continues to be debated in the scientific community, it offers a profound reminder of how our understanding of the universe continues to evolve. From Newton's absolute space and time to Einstein's relativity, from the static universe model to the expanding cosmos, and now to the recognition of light's cosmic limitations, each step has revealed a universe more vast, complex, and counterintuitive than we previously imagined. Perhaps the most mind-expanding aspect of this realization is what it suggests about human knowledge. Our understanding of the cosmos has always been limited by what light can tell us. The photons that reach our telescopes and detectors carry information about the observable universe. If light can only access an infinitesimal fraction of what exists, then our scientific picture of reality, impressive though it is, might be equally limited. As we gaze at the night sky, watching the ancient light of distant stars, we are seeing only a tiny pocket of a much grander cosmos, a cosmos where light itself, the fastest messenger we know, might truly be the slowest thing in the universe.